Nishuhudia hapana, hiyo tu nilikuwa nimeambia
All I could do was hold you. Only made us closer. Put it all behind me. Shouldn't I? But I see in the back of my mind. Oh,
Yes, Bwana Wachira, good morning.
Morning.
Hello.
Yeah, nasikia madam.
Okay, so let me proceed. So good morning, everybody. Welcome to today's physics lesson. And we are going to revise the Mokasa paper 2, which I'm sure that everybody has the paper. So we start with section A. Question number 1. Allow me to share the paper online so that we discuss as we have a look at the questions. So I'm sure you can see the marking scheme. We start with question 1. The figure below shows a ray of light being incident on a mirror. Part A, complete the diagram showing the reflected ray. So anything to do with geometric objects, you use any ray drawn to have an arrow. So because this ray is incident to the mirror at 90 degrees, it means it's thing. So the moment it strikes the mirror back through, it's reflected through the same path. So Sorry, I think there was a problem with my network, but I'm back. So the angle between the incident ray and reflected ray and normal is 0, just like the angle between the normal and reflected ray is also 0. Number 2, we have a graph that shows a variation over U against 1 over V. But takes place in front of a concave mirror. So this is usually the graph. I think what you have on your paper has a line that is hanging. So what is to do is to take a ruler and extrapolate the line, ensure it cuts both vertical and horizontal axis. Then you will find that in most cases, in such a graph, the y-intercept is the same as x-intercept. Even if they are different, you find that they are slightly different, or the difference is very small. Usually, focal length equals to 1 over the y-intercept. Focal length equals to 1 over y-intercept, or focal length equals to 1 over x-intercept, since the two are the same. But then because graphs whose y-intercept is different from x-intercept, that's why we now opt for the summary, where focal length will be 1 over average of the two. So 0.06 plus 0.06 divided by 2 gives us 0.06. And our F will be 16.667 or 16.67. Then apart from this graph, also understand a graph of M against 1 over against V. A graph of M against V, the focal length equals to 1 over the slope. And then we also have a graph of UV against U plus V. So you need to know all those, both for mirrors and thin lenses. It is the same. Number 3, basic law of electrostatic charges. Like charges repel and unlike charges attract. And before you answer this question, be very keen, because we also asked about the basic law of magnetism. So you have to be keen. Page 2, positively charged rod is brought near the cap of a lightly charged electroscope. The leaf divergence fastens, and as the rod comes near, diverges more. State the charge on the electroscope. So definitely the charge on the electroscope is negative. That's why the leaf diverges, reduces as the rod approaches, because these negative charges are being attracted from the upwards to the cap. That's why it collapses. Then to explain the observation, electrons are being attracted by positive rod from the leaf to the cap. Avoid this word neutralized. They are not being neutralized. They are only being So we continue explanation. The first explanation is you explain why the leaf falls. And then the second one, you explain the divergence. So the first one we have already explained, electrons are attracted by positive charges on the rod. And then the second one will be excess electrons are attracted to the cup, leaving positive charges leaf and plate. Excess or more electrons are attracted to the cup, leaving positive charges on the leaf and plate. Number 4, testing on electromagnetic spectrum, where we are supposed to fill in the blanks. So we have the type of radiation. In the first one, we are told about the detector, but these are X-rays. So they are detected by photographic films, fluorescent screens. Use is given. The second type of radiation is not given. We are told is phototransistor of black matter and warmth sensor. So the warmth, anything to do with heat, is infrared radiation. B, radio wave signals can be detected behind hills in lower valleys, but TV waves cannot. Explain. The answer is radio waves have longer wavelengths than TV waves, hence they are diffracted more. They are diffracted more, and I think we know this is the process where waves are able to pass through obstacles or even around the obstacles. So because their radio waves can be diffracted more. 5, an iron rod is positioned facing the north-south direction as it hits several times. It was later observed that it using the domain theory, explain this observation. This is magnetization by use of hammering method. And what you do as you hammer, you set the dipole in vibration. So the first statement should be the dipoles are set into vibration. The dipoles are set into vibration. Then the second one, the explanation is they settle in north-south direction, or they align themselves in north-south direction, creating a magnet. So hammering process is a mechanical way of magnetization. We set the dipoles into vibration, then align them in north-south direction. Of course, they align themselves in that direction because of the Earth's north-south magnetic field. It's the one that influenced them to face in the direction. So don't say that the domains vibrate, it's the dipoles that vibrate. Number 6, maybe someone to let me know if I'm clear now. Mr. Wachira, unanisikia?
Yes, Mr. Babunga. Kwa sawa.
Niko sawa sasa?
Yeah.
Okay, sawa. Okay, so we are here on question number 6. We are given a conductor placed in a magnetic field. So of course the field runs from north to south, and this conductor shows us that current is coming out of the paper. So using Fleming's left-hand rule, we need to know the direction of motion of that conductor. So field from north to south, current out of the paper, we can see that the thumb points upwards. So the observation is the conductor moves up. That's the observation. You score the first mark by saying the conductor moves up. Then explanation, you say the interaction between the field of the permanent magnets and the field due to the electric current produces a force. Interaction between the field of the permanent magnets and the magnetic field of the current due to the current produces a force moving the conductor upwards. Anything that moves due to electric current is due to the effect of interaction between two magnetic fields or more. So you should talk about the interaction between the two magnetic fields. Then number 7 is about waves. The figure below shows a wave profile of moving, I think it's moving at a velocity of 200 meters per second. Determine its wavelength. We know wavelength is distance between two successive crests or distance between two successive troughs. So if we pick two successive troughs, then we can see from here where my cursor is up to here. This is distance between two successive crests. But whatever that is on x-axis is time, not distance. So we have to find the periodic time. We have to find the periodic time, which is time taken for one complete cycle. From here to here is a complete cycle. So 0.06 minus 0.02 gives us 0.04 seconds as our periodic time. Then we know that frequency equals to 1 over t. When we substitute, we get frequency as 25 Hz. Then after that, we apply the wave equation. The wave equation says V equals to lambda F. V equals to lambda F. And V is given as 200 meters per second. And F is 25 Hz. So substituting, we get lambda to be 8 meters. Remember, C is used if it's an electromagnetic radiation. So the distance between two successive crests or troughs will now be 8 meters. Now we move to number 8. Distinguish between a transverse and longitudinal wave. The word is distinguish. It means you give the meaning and not any other difference. So in transverse waves, vibration of particles is perpendicular to the direction of wave motion. Longitudinal waves, vibration of particles is parallel to the direction of wave motion. So that's the meaning of those two waves. Here we have a longitudinal wave. The figure below shows a longitudinal wave. Show on the diagram the wave region of 1, low pressure. Low pressure is region of, it's a rarefaction where the wave fronts are far apart from each other. High pressure is a compression where the wave fronts are close to each other. So this wave transfers energy because of movement of low regions of low and high pressure. In case you're asked about wavelength of such a wave, then you take one complete rarefaction, combine it with one complete compression. For example, it will start from here where my cursor is, starts from here up to here. That's wavelength. Alternatively, you can take 2 halves of rarefactions and one complete compression. So a half of this will start from here, and then a complete compression, then end here, half of the other rarefaction. Number 9, a student was investigating the brightness of bulbs when set up in electric circuits. She used identical bulbs and cells. The circuits shown in figure 3A and B were what she set up. So we have A, this is bulbs in series, B, bulbs in parallel. Which setup was the bulb brightest? Give a reason for your answer. So of course, B will be brightest. Reason being, when arrange bulbs in parallel, then their net resistance is very low. So this setup has lower resistance to the flow of current. Suppose these were resistors, then we will have the total resistance will be 1 over R total equals to 1 over R1 plus 1 over R2. The answer we get will be less than these ones because these ones we add directly. So opposition to flow of current here is low. Here is very high. That's why bulbs should be arranged in parallel in any domestic wiring process. Again, the 2 bulbs receive equal voltage, which is voltage of the source. So if this is 3 volts, each bulb here receives 3 volts. On the other hand here, A, if this was 3 volts, it's going to divide itself into 2 according to the proportions of the resistance of these bulbs. Suppose this is 3, then you will find that this is probably 1 volt, this is 2 volts. That is section B. Number 10, define interference of waves. This is superpositioning of waves traveling in opposite directions. Not opposite. Superposition, just say this is superpositioning of waves when the waves meet. I think the way it's written is okay. The other one that I was trying to define is formation of stationary wave. But this is interference. So superposition of waves traveling or the superpositioning of waves when they meet So here we have a process of interference in light. The figure below shows waves of monochromatic light incident on two adjacent slits S1 and S2. P is the first bright fringe, this one here. After the central bright fringe, the central bright fringe is this one in the middle. So this is the central bright fringe. Of course, the central fringe is always bright. Then the first bright fringe we are told is P. Now, when we talk of monochromatic light, it means light of the same color. Monochrome, light of the same color. Usually it has the same wavelength, same frequency, and also speed. Now, what is the purpose of slits S1 and S2? These two act as coherent sources of light. You can also be asked, what is coherent sources of light? These are sources of light with the same wavelength, same frequency, same speed, and almost equal amplitude. When it comes to amplitude, you say almost equal amplitude. Doesn't have to be the same. State and explain the observation made. What we see on the screen here is alternating. The word alternating is a must. Alternating bright and dark fringes. Bright fringes because of constructive interference, and dark fringes due to destructive interference. This is the explanation. Then part B, state what is observed on the screen when slit separation D is reduced. When we reduce this D, S1 to S2, then the fringe separation increases. So this is not right here. Write it as fringe separation increases when we reduce D. When we increase D is when the fringe separation reduces. It's the opposite. Excuse me. So you can find other books talking about number of fringes. When we want to talk about number of fringes, then you say slit separation D is reduced, then the number of fringes also reduces. Number of fringes reduces on the screen. But when we want to talk about fringe separation, then it increases. Roman 2, distance X is increased. When we increase X, then the fringe separation increases also, or number of fringes decreases. When we increase X, fringe separation increases. When we replace the monochromatic light with white light, remember what we are saying here is S1 and S2 are producing either red, blue, or yellow, or green, or orange, or indigo. One of them, that's monochromatic light. But when we replace this with white light, the normal light, then what we see on the screen is colors of the rainbow. A band of 7 colors of the rainbow are seen on the screen. with the brightest at the middle. So this thick line here in the middle will be the brightest. Then we have bands of the colors of the spectrum up and down. Give an expression for the wavelength lambda of light. Okay, this question is about path difference, but path difference is not tested in the current syllabus. But you need to understand the distance from S2 to P. Remember, P is the first bright fringe after the middle fringe. So from the central bright fringe to the first bright fringe, distance from S2 to P minus distance from S1 to P gives us lambda. Distance from S2 to P, that's why you can see this formula here. S2P minus S1P equals to lambda. But you don't have to really measure on that because it's out of the syllabus. Question 11. Define critical angle. This is the angle of incidence in the optically denser medium. The word optical is missing here. Angle of incidence in the optically denser medium whose angle of refraction in the optically less dense medium is 90 degrees. Angle of incidence in the optically denser medium of which or whose angle of refraction in the optically less dense medium is 90 degrees. So that is the critical angle C. B, we have a student had a research project of making a fiber optic cable as shown. 1, compare with the reason the optical densities of materials A and B. So A we can see is the inside here, I think is glass or some optic material. And then B we can see it's the casing. This casing is called cladding, the outward protective layer. Now, A has a higher optical density than B. A has a higher optical density than B. Remember, as light passes through this optical material, it must suffer what we call total internal reflection. So it appears as if it's coming out of the material, but then because the angle of incidence is higher than the critical angle, it suffers total internal reflection. That's why it keeps on bouncing to the edge of the material until the other end. So A has a higher optical density than B. This is to ensure that total internal reflection takes place inside the material. Remember that total internal reflection takes place in the material, not outside the material. Maybe just to add, one of the conditions for total internal reflection to occur, which is supposed to take place here, is light must be traveling from optically denser medium towards optically less dense medium. That's why A should be optically denser than B. 2, on the diagram, draw the path of a ray of light incident on the cable at point P till it emerges. So you use a ruler. Remember, this is geometric optics. Your rays should have arrows using a ruler because light travels in a straight line. So you draw those zigzag rays until Q. Then C, the figure below shows a ray of light passing into a glass prism ABCD. Sketch the path of the ray as it travels from face AC, Now, any ray that you're supposed to draw, let's say whether it's in refraction or reflection from one, you must use a ruler and your ray should have arrows. So this was the initial path of the ray, striking AC at 90 degrees. No reflection takes place because this is a transparent material. So it enters the prism through 90 degrees and strikes this edge. Something else you should do is you must show all the angles. All angles should be shown. For example, this diagram here, it's not complete because this angle has not been shown. The angles here have also not been shown. So how do you know that this ray is supposed to come out here? So first of all, we investigate what is the angle of incidence here. So when it strikes this edge, CB, we draw a normal. Since this is 90, this is 60, it will be automatically 30. Angles and plane figures, mathematics. Angles in a triangle add up to 180. So 90 plus 60, this is 30. Therefore, the angle of incidence here will be 60. And I equals to R. Before I equals to R, 60 is greater than the critical angle. Because we can see the critical angle here is given as 42 degrees. So since I is greater than greater than C, then we must have total internal reflection here because the angle of incidence has exceeded the critical angle. Then we say now 60, I equals to R from the laws of reflection. And if this is 60, then the remaining angle here will be 30. So that we have 30 plus 60 plus 60 plus 30, total 180. And this is given as 30. So we find out which angle is this one here. So 30 plus 30 gives us 60. From 180, we remain with 120. So this is 120 degrees. Then we draw the normal here. You draw a normal here. Of course, a normal is 90 degrees to the interface. Therefore, we find the angle of incidence here, which will be what? The angle of incidence will be 30 degrees at this point. And since the angle of incidence will be 30, 30 is less than 42 degrees. Therefore, we cannot have total internal reflection. Instead, we're going to have refraction taking place. So the ray emerges outside into air. You are also supposed to tell which angle is here, which angle of refraction is here. So you will say sine I over sine R equals to the refractive index, which is 1.5. Therefore, sine theta here over sine I, which was 30, equals to 1.5. And you get this angle as 48.59. So this ray comes out with 48.59 degrees to the normal outside here. So that's how you answer that question. Number 12. The figure below represents two parallel plates of a capacitor separated by a distance d. Each plate has an area of S square meters, square units, sorry. Suggest two adjustments that can be made on the plates so as to reduce the effective capacitance. We know the factors affecting the capacitance of a parallel plate capacitor, one of them being distance of separation D. So for us to lower the capacitance, we increase that distance D. So here, one of the answers says, move the plates away from each other or increase D. Then another factor is area of overlap. But you don't mention area of overlap because the question is very specific. It requires you to change those factors to suit this context. So you displace the plates sideways so as to reduce the area of overlap, not contact. Displace the plates sideways to reduce the area of overlap. Then, in terms of the dielectric, you may not talk about the dielectric because here we are using air. So we are not changing the air, it's still there. Part B, the figure shows a circuit diagram with 3 capacitors. Determine the effective capacitance of the arrangement. So you start with parallel, 3 plus 2, that is 5 microfarads. Then series, product over sum, 5 times 4 over 5 plus 4 gives us 2.222 microfarads. That is 20 over 9, product over sum, 2.222 microfarads. Roman 2, we are asked to find the PD potential difference across the 2 microfarad capacitor, this one here. So first of all, we need to know how much charge is moving in this circuit. So the total charge Q is given by CV. Our C is 2.222 and V is 6 volts. So we get the total charge to be 13.33 microcoulombs. It is this charge that determines the voltage across each capacitor. So if you want your work to be very easy, deal with this one, these 4 microfarads. It's the easiest to deal with because it's alone. It's not sharing with any other capacitor. So you find how much voltage is here. So voltage equals to Q over C, which is 13.33 divided by 4. Of course, I'm using microfarads, and for the capacitance, I'm using microfarads. For the charge, I'm using microcoulombs. Let's listen to Abdul. Yes, Abdul, you can speak.
Hey, hi, teacher.
Yes, hi, how are you?
I'm good, thank you. Me, I have a question.
Yes.
If you use the Pythagoras theorem to find the ratio of A to B, then how will your answer circumnavigate the Earth through the crust?
I don't understand that question. Maybe you repeat yourself. Because Pythagoras theorem is talking about Pythagoras theorem and circumnavigation of the Earth. I don't know. I've not understood your question. So Here we take 13.33 times 10 raised to power negative 6 over 4 times 10 to power negative 6. And we get the answer, voltage across the 4 microfarad capacitor as 3.333 volts. But the question is asking, what is the PD across 2 microfarad capacitor here? So we are now going to take the 6 volts total voltage minus voltage across the 4. So 6 volts minus 3.333 gives us 2.667 microfarads. So this 2.667, this should not be microfarads, but volts. 2.667 volts is the one that dissipates itself here on the 2 of them. Because they are in parallel, they will have equal voltage. Here we have 3 here the voltage will be 3.333 and here will be 2.667. That's how the voltage splits. Yes, Joe. Joe?
Hi, teacher. I don't understand what the other question was, and I'd kindly like to understand.
What he has just asked.
Yes.
I also didn't understand because it's out of context. It's out of what we are talking about.
Oh, okay.
Yeah, he was asking about, I think, things to do with the acceleration of the Earth or something.
Oh, okay.
Which is uniform circular motion. Yeah. I think he's just trying to be a comedian. So
Okay.
let's proceed. Yeah. So here, I hope we have understood how to get the voltage distribution over here and here. Now, in case you're asked about the charge distribution, a capacitor that is alone like this one will receive all the charge in the circuit. So all the charge in the circuit will be through 4 microfarad capacitor. Here they will share in their proportionate ratios. Like this one will be 3 out of 5. The charge here will be 3 out of 5, and here will be 2 out of 5. C, state 1 application of capacitors. We have so many uses of capacitors, one being a car flash indicator uses capacitors, reducing of sparking in an induction coil. Then we have the camera flash unit. We also have areas like rectification. We use a capacitor to smoothen the DC output in rectification. That is changing AC to DC. Question 13. State Faraday's law of electromagnetic induction. Of course, this Faraday's law summarizes the factors affecting the magnitude of induced EMF in electromagnetic induction. So the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux linkage. The magnitude of induced EMF is directly proportional to the rate of change of magnetic flux linkage. Just the way it is, the way KLB puts it out is the same way you say. Then we have a setup here where we have a coil placed inside a magnetic field Yes. Jao, you can unmute yourself.
I have a question on that Faraday's law.
Yeah. You are the same, Abdul.
See,
Can you
you've
clarify
just
the question? The question you asked, what was that?
Oh, sorry. I got my answer. Sorry, but now I have a different question though.
Was it about what I was talking about?
Yeah, they relate. It was a relation question.
Oh, okay, go ahead.
So I don't know if this is in the syllabus, but based on that Faraday's law,
Yes.
it says that when you change magnetic field, it induces a current in a wire, correct?
Yes.
So now, in that same law, does that mean if you shake a magnet near your phone charger, see your phone charger has electric current. So if you shake a
Yes.
magnet and then that magnet induces current, in that phone charger, will it charge your phone?
Yeah, it charges because, we have factors affecting the magnitude. You see, even this law is saying the magnitude of induced EMF. It is the value of that induced EMF depends on how many factors, 3 of them. One of them is the rate of change of magnetic flux linkage, which is the speed. Number 2 is the number of turns of a coil. Then number 3 is what? The strength of the magnetic field. So now back to your question. It depends. What is the strength of the magnet you are using? If it's a very, very strong magnet, then it will affect the charging process. Actually, you will be able to see that it interferes. The induced current will interfere with the DC that is passing through your wire. If it's a very strong, yeah.
Okay, so thank you. Yes, thank you, Mr. Yo, Mr.
Eh? Check the host, check the presenter, you will see my name. Okay, thank you for that question. Let's listen to Njao.
Excuse me, teacher.
Yes.
I tried doing the same thing that Abdul was saying, but it blew up my charger and my phone.
Yes, yeah. That's why I'm telling him, if you are using a very strong magnet, it's going to induce a very heavy, more current that interferes with the normal DC output that is coming from the charger. Okay, so that interference, remember that charger has a capacitor, right?
Yeah.
Just the same way we did electronics, we talked about smoothing of the DC output. We have a capacitor inside there. That capacitor has a limit. So if you pass a very strong current, then what will happen? It blows up. We also have resistors inside there. Okay. Yeah. So that's why I'm telling him, if you're using a very strong magnet, then it will affect the charging process. And you have given the answer. One of them, it blows. Okay.
Okay.
Yeah. So. Okay. Let's proceed. On the diagram, indicate the direction of flow of current. Now here, remember, this is not a motor, so we use the dynamo rule, which is the Fleming's right-hand rule. So we are told that when the coil is slightly rotated clockwise, we are rotating this clockwise, that direction, about its axis, the galvanometer deflects momentarily. So let's choose the right-hand side of the coil, this side, towards the south, next to the south. So field north to south, using the right hand, not left. Field north to south. Force is downwards because we are told it's clockwise. Then we can see that the second finger points from this side towards where we are, towards the galvanometer, this way. Then on the other side, the left-hand side of the coil, it will point in the opposite direction. So I think there are many arrows here. I think somebody who was trying to figure out the direction, but it should only be 2 arrows, one pointing this side, another pointing the other side on the left. So that's 1 mark for Roman 1. Roman 2, explain why the galvanometer deflects. Anytime you are asked a question regarding electromagnetic induction and you are asked why we have an EMF induced, you must mention the term change in magnetic flux linkage. So here, when we rotate that coil, the conductor cuts the magnetic field, causing a change in magnetic flux. That is a marking point. Change in magnetic flux causing an induction of an EMF. An EMF is induced. So when an EMF is induced, it causes a current to flow. So the conductor cuts a magnetic field, causing a change in magnetic flux linkage that produces an EMF, causing a current to flow. It's an EMF induced that causes a current to flow. Let me respond to a few questions here. Let's start with Beshe. Yes, Beshe. Beshe. I think he has disappeared. Let's go to apps.
Excuse me, teacher.
Yes.
So what will be the direction of flow of current in that coil?
The direction of flow of current in the coil,
Yeah.
I have said that on the right-hand side, this side, it's going to come towards, the direction points towards the galvanometer, this way. You see the red arrow?
Yes.
The red arrows are the ones showing the correct direction. So, yeah. Hope that's okay. Let's listen to Wilson. Wilson. Yes, Wilson. Wilson, we can't hear you. I've seen you have unmuted the mic, but we can't hear you. Check your connectivity, Wilson. Can't hear you. Yes? Wilson is even listening to music, so he's not a serious man. Okay, let's proceed. So I think we have explained why the galvanometer deflects. Make sure you mentioned change in magnetic flux linkage that produces an EMF which causes a current to flow. In whichever case you are being tested, whether it's a magnet moving towards the coil, talk about change in magnetic flux linkage that produces an EMF causing a current to flow. Roman 3, state and explain how the deflection will be made larger with the same apparatus. So we are being asked on the factors affecting the magnitude of induced EMF. One of them, we said, the rate of change of magnetic flux linkage, which is the speed of rotation. So we increase the speed of rotation because the question is asking for larger current to flow. So increase the speed of rotation. Then number 2, we may not increase number of coils, but we can also, explanation. So increasing the rate of change of magnetic flux. Then explanation, you say, increasing the speed will increase the rate of change of magnetic flux, linking, of course, the conductor, this coil, and the magnetic field of the permanent magnet. Then C, we have an induction coil. The diagram below shows an induction coil used to produce sparks in a car ignition. Explain how the sparking is produced when the switch is closed. First of all, you should know the work of this device. This is a device that is used to switch on a petrol air engine. It can be a car engine, it can be any industrial machine engine, but the main aim is to produce these sparks, which are now used to start the engine. So before we start, you need to know that it produces sparks due to a higher EMF induced in the secondary. And for us to produce a higher EMF in the secondary, we must have a higher change in the magnetic flux. And we have two things happening here, connection and disconnecting. When we connect here, this contact here is going to break, disconnecting the same circuit. So you need to ask yourself, between connecting and disconnecting, where do I have a higher EMF induced? Is it by building up current, connecting, or disconnecting, that is current dying off? And you find that current, a higher EMF is induced is off than when it builds up. So the whole system is designed so that a higher EMF is induced in the secondary coil C when there is a breaking of the contact here. So you start by saying, when the switch is closed, the soft iron rods are magnetized. These are soft iron rods. They are magnetized because remember, current flows in the primary. The primary coil here is A. The one on top, you can see it has fewer turns. So the soft iron rods are magnetized, attracting the soft iron armature. This is the soft iron armature here. That's the first mark. Wilson?
Teacher, is this the system that is in the spark plugs of a car?
Yes, it's the same system.
Okay, thank you.
Yeah. Okay, so When this becomes a magnet, it attracts the soft iron armature. That's the first mark. Second mark, the contact here, this is the contact, breaks. So when the contact breaks here, what will happen? Current stops moving. It stops flowing. So the contact breaks, stopping current from moving in the first circuit here. Then what happens next? The soft iron rod or rods are demagnetized. Hence, the soft iron armature goes back to its original position. So as it goes back to the original position, the contact will be made again. So the process keeps on repeating. But what you need to say is when the switch is closed, the soft iron rods are magnetized. The soft iron armature is attracted to the electromagnet, breaking the contact. So during that process of breaking the contact is when we have now current dying off. So after that, you say the current dies off from maximum to 0. That is after the contact is broken. Current dies off from maximum to 0, causing a change in magnetic flux that induces a higher EMF. Current dies off, causing a change in magnetic flux that induces a higher EMF in the secondary coil C. Remember the word higher EMF in the secondary coil C. The current that flows in the secondary coil produces sparks that can be used now to ignite an engine. The current that flows in the secondary coil C produces sparks that can be used to start a petrol air engine. Let's listen to Z. Yes. Yes, you can speak. We can't hear you. Make sure your connectivity is well. So let me repeat. When the switch is closed, the soft iron rods are magnetized. They attract the soft iron armature. The contact is broken. Current dies off from maximum to 0, causing a higher or inducing a higher EMF in the secondary. The current that flows in the secondary produces sparking. That's all. So this process continues until the switch is opened. State the purpose of B. B is a capacitor, and it's used to reduce the sparking at the contacts. Don't say prevent, reduces sparking at the contacts. Number 14, this is main selectivity. Electrical energy is distributed in grid network using thick aluminum cables as AC at high voltage. Explain why. 1, a grid system is important. It's like being asked, what is the use of a national grid system? So the national grid system is important to ensure continuous uninterrupted supply of power, continuous uninterrupted supply of power countrywide, even if some power stations are shut. So any power generating company or farm feeds its output to the national grid system, so that we have everybody across the country accessing power. Even if the stations next to these people have been shut, probably for maintenance, people around that area should receive power as the work of a national grid system. 2, reason for very high voltage is not to prevent power loss, is to minimize power losses. Minimize power losses, because we can see power equals to I squared R. And the moment we boost the voltage, current goes down. So when current goes down, the power lost becomes minimal. 3, the power is transmitted as AC. AC can be stepped up or down. AC voltage can be stepped up or down. You can't step up DC voltage. You also can't step down DC voltage. It's not possible, because we must have a continuous change in flux linkage. Then 3, a laminated core is used in transformers. This is to prevent eddy currents. Eddy currents are the currents that are induced in the soft iron core that interfere with the normal flow of current in the coils. So to prevent that, we laminate the core. We put so many sheets of soft iron together. B, the figure shows part of a domestic wiring system with a fault. So we have the connection here. I think this was a fuse. It's only that I think something happened during printing, but this is a fuse. So identify the fault and draw another diagram besides it with a correction. So the fault is the switch is placed on the neutral. All switches in an electric circuit must be connected to live. All switches and all fuses should be on live wire, not neutral. So this is the correction. Roman 2, state the function of part F. F is a fuse, and the main work of a fuse is basically to protect the appliances against electric surge, excess current, to protect the appliance against electric surge or excess current. Then you can add and say that it melts, hence breaking the circuit in case of an excess current. Part C, we have electric costing. Electric costing is over there. We can go through the total
Hello.
Okay, so I think we can see that for the heater, we have 4 kilowatt hour. Iron box is 0.75, bulb is 1.5. So total we have 6.25 kilowatt hour. These are units, 6.25 units. So when we multiply by 30, because it's for 1 month, we get 187.5 units in that month. And 1 unit is 12 shillings and 50 cents. We multiply and get 2,343.75 shillings. Then we have standing charge. Standing charge is whether you have used electricity or not, you will have to pay that amount, which is 300. So we add and get 2643.75. Then after that, we have fuel cost. Fuel cost, which is 90 cents per unit, and we have 187.5 units times 90 cents. It gives us 168.75 shillings. So total 2812.5 shillings. So that's what this person pays. Number 15, distinguish between a real and virtual image. The word is distinguish, not differentiate. So we talk about how they are produced. So a real image is produced by intersection of real rays, while a virtual image is produced by intersection of virtual rays. Here we have a ray diagram. We have an object O between F and 2F in front of a lens. So the question says, by drawing appropriate rays on the same figure, show the position of the image formed. So geometric optics, ruler and arrows, especially that part for arrows, most of us, we are forgetting. Make sure you after drawing the ray, show that it's a light ray by putting arrows. So the first rule that we use is a ray parallel to the principal axis is refracted through the principal focus on the other side. So it comes this way. The second law is a ray through the optical center is not refracted, so it goes straight. So we get an inverted magnified real image on the other side of the lens. You can also draw a third one in case, although you need only 2, another third ray can pass through the principal focus, strike the lens, and then it will be refracted parallel to the principal axis. So it will still come at this point. Yes, Abdul.
So
Yes.
under the same topic of this topic is a topic in Form
Yes.
2 we did called refraction, and for curved surfaces.
Yes.
Can you, but I didn't fully understand it. Can you like clarify how the rays are supposed to pass?
Okay. First of all, the main difference, the major difference between lenses and curved mirrors is anytime you are drawing those rays, you should know that this is refraction. Anything to do with a lens is refraction because it's a transparent material. So light passes through straight. But when it comes to Form 2 work, which is mirrors, is reflection. Light strikes the mirror, then goes back. Like if this was a mirror, we wouldn't be having F and 2F on this other side. It's not there. It's only on one side. So like this ray will have come, it strikes here and then goes back through F. This one will have come, strike here at the optical center, then goes back at the same angle. So for the lenses, it's refraction. You pass the rays through it to the other side. For the mirrors, reflection. The rays should go back. So you will find that the difference in terms of rules of reflection and refraction, here we only have three. A ray parallel to the principal axis is refracted through F on the other side. A ray through the optical center is not refracted, it passes straight. A ray through the principal focus is refracted parallel to the principal axis on the other side. In mirrors, we have four. A ray parallel to the principal axis is reflected through F. A ray that passes through the center of curvature, let's say this was C, it goes, strikes the mirror, then comes back through the same path. Then a ray through F is reflected back parallel to the principal axis. Then lastly, a ray that strikes a mirror at the pole goes back at the same angle. Those are four rules. But here we have three rules only. So I hope you have understood.
Yeah, thank you.
Sawa. Okay. Now here we have a question. An object is placed 20 centimeters in front of a diverging lens of focal length 10 centimeters. Determine the position of the image. Before you do any calculation, substitution, think about what is virtual, because this question tests whether you understand real is positive. For example, this is a diverging lens. A diverging lens has a virtual principal focus. So the focal length is virtual. This 10 is minus. So you write the normal way we write the formula. Don't start introducing negatives at this level. Then substitute F will be negative 10. U remains 20. Then you find V, where V is now positive 6.667 centimeters. So these are the cases where we have negative signs. Any virtual image, if you're told it produces a virtual image 10 centimeters from the mirror or from the lens, then that virtual image you must attach a minus sign because it's virtual. Number two, focal length of a diverging lens. A diverging lens ni kama hii imechorwa hapa chini. Or it's called concave lens. Focal length of a concave lens is also negative. Then number three, focal length of a convex mirror. Focal length of a convex mirror is also negative. So those are three cases: virtual image, focal length of a concave lens, and focal length of a convex mirror. Those are the areas you attach a minus sign. So here we have an eye defect. The defect is myopia or short-sightedness. Then correction, we use a diverging lens. As you draw, remember, ruler and arrows. So you should show that this lens has diverted this initial lens rays. You should show that they have diverted a bit. Don't just ignore that. It should be seen. Then converge on the retina on the other side using a ruler with arrows. So I hope we have enjoyed the lesson. Thank you for the questions. Thank you for cooperation. We meet again tomorrow. I don't know if it's tomorrow or Friday, but Have a good day. David, can see you have a question. Yes, David.
Yes, I was asking if you can repeat on the topic of magnitude.
Topic of?
The Paradise law, that topic, next lesson.
Oh, you want to be taught the electromagnetic induction.
Yeah.
As a whole topic.
No, just the question.
Or the question. Okay.
Yeah.
Maybe I will sample a question so that we discuss more on the same. Sawa. So you can leave the meeting.